The Baeyer-Villiger oxidation is our last oxygen reaction that we're going to do in this class. It's not with the oxygen nucleophiles, simply because the Baeyer-Villiger oxidation is oxygen inserting into an aldehyde or a ketone between a carbonyl and a neighboring group. And so an aldehyde or ketone is actually converted to a carboxylic acid or an ester, right? If you have an aldehyde, it's converted to a carboxylic acid. If you have a ketone, it's converted to an ester. Let's look at this reaction mechanism. You use a peroxy acid, one of my favorite functional groups. Remember, the peroxy acid looks very similar to a carboxylic acid, but it has a peroxide bond in it. So that highlighted red oxygen is the most reactive oxygen, not only because it has the acidic proton, but it also has a peroxide bond, which is very, very reactive. That oxygen will attack the carbon of the carbonyl, kicking up the lone pairs onto our oxygen. And then we will do an intramolecular proton transfer between the protonated oxygen and the oxygen of the peroxy acid carbonyl. That shouldn't be too big of a deal for us to do an intramolecular reaction. Intramolecular proton transfers are not good, we'll see later on in later chapters, unless we do have 5 to 6 atom spacing, right? So we do need that proximity to be between 5 to 6 atom transition states. So here we have 5 member transition states. And so later on, we'll see where these reactions of intramolecular proton transfers might not occur because it's less than 5 membered transition states. 5 and 6 is always great because remember, those are the most stable cyclic structures. And so that's where we're hinting towards this 5-membered ring transition as a more stable approach. Okay. And then we get a rearrangement. Oxygen from the ketone or the aldehyde relaxes back down, and we actually get the rearrangement of one of the neighboring groups, either the R groups or the hydrogen, whichever one of these. Let's highlight them. It's one of these two, right, that get rearranged, and they will pop over to the peroxy acid oxygen, the one that's still highlighted red. That will cause the detachment of the rest of the peroxy acid, very similar to epoxidation way back from chapter 8. So now we have inserted an oxygen in between the carbon of the carbonyl and one of the neighboring groups. Cyclic ketones produce lactones, which are actually really, really important for biology. For aldehydes or unsymmetrical ketones, the rate of migration is this. Usually a hydrogen will migrate first, it's the smallest. Then a tertiary, primarily the reason for the tertiary moving is because of its carbocation stability, all right? Secondary, and then a phenyl group. pH is a benzene ring, phenyl, and then primary, and then methyl. So use this trend to determine the regioselectivity, who's going where, okay? We can see that trend in a couple of examples. Let's just look. We have this group, or the primary, essentially, it's a primary on the right-hand side versus a tertiary on the left. Tertiary, primary. Which one is better? The tertiary. So Baeyer-Villiger oxidation will take and put an oxygen there. Same thing, we have a phenyl versus a hydrogen. Hydrogen is most likely going to move. So this is a great way to make carboxylic acids from aldehydes. If you have an aldehyde, you're always going to make a carboxylic acid with the Baeyer-Villiger oxidation.